Sir, your mic is mute. Sir, your mic is mute.
The title of the lecture is Hypergeometric. Sorry?
It's okay, sir. Okay.
Oh, I do. What is this? Everyone? If I am audible?
Yes, you are audible. You are audible, sir.
Yeah, okay. Okay, so my title is Hypergeometric type extension of bivariate zeta functions. And I am dividing my lecture in the following subtitles. First of all, abstract of the title. Then I'll be talking about the zeros of Riemann zeta function. Then the Hubert or generalized zeta function. And finally, Hypergeometric type genetic functions. Now, based on the generalized extended zeta function, we have introduced and we are still using new Hypergeometric type extended zeta function together with the related integral representations, differential relations, finite series, and series expansions. Also, we find a relationship between the extended zeta function and the Lebesgue column. In fact, our Hypergeometric type extended zeta function involves several non-zeta functions, including the Riemann, Hubert, and Barnes zeta function as particular cases. Introduce Hubert zeta function first of all. We denote this by zeta ZA equal to series n equal to 0 to infinity plus n to the power minus s, when the conditions for a real part of z are given, and this is in fact a generalization of the Riemann zeta function, which is denoted by zeta z and is simply a series n equal to 0 to infinity n to the power minus z. Here and elsewhere, we will be having the notations which are well known for the complex real and others, positive integers and so on. And we are very much clear with these notations. When a generalization of both Riemann and Hubert zeta functions, the so-called Hubert zeta or Hubert left zeta function is defined in the following way. This is denoted by phi yza equal to c equal to 0 into d by to the power n upon a plus n to the power z, together with the conditions for a and y. Here phi is an analytic function in both variables y and z in a suitable region. If suppose we substitute for y, then for phi will change in the following way, and the right hand side will be simply giving the series having numerator e to the power twice by iota n lambda and denominator j plus n to the power z. Now, first of all, let us consider some more particular interesting aspects of Riemann zeta function. So, for this purpose, this zeta s is considered again. This Riemann zeta function in the above form was first encountered in the study of complex function in 1359. That means almost 160 years back. And is important due to its remarkable connection to other fields in mathematics, especially as a number theory and multi-theory, and primarily through the Riemann hypothesis. When we consider the Riemann hypothesis, then this hypothesis is in fact a famous hypothesis is depending on zeros of Riemann zeta function. The values x and z when this zeta s attains 0 are called zeros of the function. One can easily deduce that zeta s equal to 0 when s is given by negative even integers 2, 4, and 6. Now these are zeros, but we can see that these are in fact trivial zeros, since they have much smaller significance. Therefore, we are not having any importance in research of these zeros, but the rest of zeros are all at the critical strip in complex plane, which is the strip of complex numbers with the real parts of S between 0 and 1. Now these zeros are called non-trivial zeros, and their distributions is an important topic in analyzing number theories and prime number distribution. In mathematics, the Riemann hypothesis is a conjecture that the Riemann function has its zeros only at the negative even integers and the complex numbers with real parts are. And here again, I emphasize that this real part of will be coming again and again when we are applying Riemann zeta functions for the applications in number theory, partition theory, and other type of multidisciplinary subjects. It was proposed first of all by Riemann in 1859 after it is named as a Riemann hypothesis. Next we recall the further development of the Riemann zeta function in the following form, and this is having the notation which is y mu star x z a equal to series mu n x to the power n upon a plus n to the power z. Here this alpha n is complement symbol, the Riemann complement symbol, and is denoted by gamma e plus n upon gamma a, and symbol is such that mu is contained in the together with the conditions for a and x. Obviously, when mu is equal to 1, then 1.5 reduces to 1.3. Now, orbits, or sometimes we say generalized zeta function, zeta s a is simply written as a series with the numerator 1 and denominator a plus m to the power s, where conditions are given for s and a, and this a should not be equal to 0, minus 1, minus 2, and so on. But just as the Riemann zeta function zeta s can be continued parabolic everywhere in the complex S plane except for a simple pole with residue 1. From this, definition we have zeta S1 equal to zeta S, and this is also written in terms of zeta S up. So here, whatever zeta function you will take, you will think about that whatever value you will use for A, the important value is always a equal to r. And for this purpose, this revealed data function is having wide number of applications. This is connected to many other special functions, and the most important function of this revealed data function is in the form of Bernoulli polynomial. Bernoulli polynomial B and A is defined in the following way that T upon T upon T minus 1 T raised to the power x T is equal to series B and x T raised to the power T about factor n. What is B and x is Bernoulli polynomial, and this B n is simply Bernoulli number. Now the zeta minus n A can be written in terms of a n plus 1 a upon n plus 1 and n is equal to 0 1 2 a and so on, which is for a equal to 1 will be inverse zeta minus n is equal to b n plus 1 upon n plus 1, which is very important given number theory. And here the zeta function is given for negative integers, where b n denotes Bernoulli number, which is of Bernoulli polynomials b and x and defined as follows. Now the unified zeta function while ZSA is defined in the following way. This is again the series, infinite series. The numerator is z to the power n, and denominator a plus m to the power s, with the same condition out of z less than 1 and a should not be equal to 0 minus 1 minus 7. And this can also be represented in terms of integer. And this integer representation is again very important, because by changing this integer into number of ways, you can just find out various integers involving unified zeta function. And this unified zeta function is simply a case you just substitute z equal to 1, you will be getting zeta SA from this unified zeta function. Moreover, next, because this has very important connection with the Bernoulli polynomials. So, what about having some introduction of hypergeometric Bernoulli polynomial? Yeah.
सर आवाज थोड़ा क्लियर नहीं आ रहा सर, आवाज तो माइक्रोफोन के थोड़ा पास में आवाज क्लियर नहीं आ रहा।
क्लियर नहीं आ रहा, एक मिनट देखता हूँ मैं क्या हो सकता है।
माइक्रोफोन के पास में आके बात बोलिए तो साफ आएगा।
Not suitable?
Yeah.
Sorry.
Yes.
Okay. So the better way to connect this Bernoulli polynomial to Riemann zeta function is through hypergeometric function. And for that purpose, we have to define this hypergeometric Bernoulli polynomials. So for that, there is one paper which is written by me and published in Statistical Mathematics in the year 2018. This is the paper which is on unified PQ Bernoulli polynomials. So to understand this development, first of all, you have to know about this generalized Gaussian hypergeometric series. This is a well-known series, and here just you can see that we are having this series in terms of the parameters and variables. Here this is one variable, so only z is introduced. Next, Next, there is a paper by Ramani, who has considered this P Bernoulli numbers first of all, and denoted by B and P. This B and P, which is a number, is also connected to this was Hypergeometric function, and this is the relation by which B and P can be connected. This is 2f1, 1 upper parameter and the lower parameter T plus 2, 1 minus e to the power t. This can be written in terms of the P Bernoulli numbers. Now remember that earlier I said about B and PQ. That means the B and PQ is a generalization of this B and P. One can see that 2f1 here denotes Gauss hypergeometric function, and this P Bernoulli numbers B and T, which are closely related to Bernoulli numbers E and, is also corrected by a formula which is about B and T, and the right hand side is simply Bernoulli polynomial, and there is a connection with the Stirling number of the first kind also. So this right hand side is containing the Stirling number of first kind as well as the Bernoulli number. So here this is Bernoulli number B and B can be connected with a series of Stirling number and B n plus j. Next, the PQ Bernoulli numbers, which I have considered, is given by this sigma B n P Q T of n about factorial. And one can see that this is also connected to Apple's function of two variables. Now, if you consider two variables as x and y, then the x and y both are equal, and both are equal to 1 minus e raised to power t. Then this Apple's function has to be with the same variables can be written in terms of the Gauss hypergeometric function, which is a well-known reduction formula, in fact, of this Apple's function. So this Apple's function is written in terms of having 2f1, 1 q plus 1, t plus 2, 1 minus et. And here, different conditions can be considered, but only one condition is sufficient here, that every TLP would be greater than minus 1. This is depending on the T, whatever may be the Q. Okay, but you will see that this Q should not be zero, because if you take the 0, then you will be getting some other type of results, not the same. But that will be a nice, interesting special case. Now, Bernoulli numbers B and PQ can also be written in terms of the finite sum. And here the right hand side you can see that this is containing the external number of second time, which is written this bracket given by nk, but in fact this is equal to e to the power t minus 1 to the power k upon factor k. So here this Bernoulli number B and PQ can also be written in terms of e to the power t minus 1. So this e to the power t minus 1 is an important part of the Hypergeometric Bernoulli numbers or Hypergeometric Bernoulli function. Now for q equal to 0, it replaces to one of the results given by Cargill and Ramani. And this is a published paper which appeared in 2018 again. And the name of the journal is given. And this B and P can again be written in terms of the finite sum. The next Bernoulli numbers we have defined. Similarly, we can define Bernoulli polymers. Bernoulli polymers again given in the paper of 2018 is given by e to the power xt 2f1, and the right hand side you can see again a series B and PQ F's e raised to the power n upon factor n for every integer e greater than or equal to 1. Now we come to the main part of our lecture, that how different type generative functions can be obtained for this Riemann zeta function. And for that purpose, I consider first of all a paper of one of my students, Majid bin Saad. This paper is published in the year 2009, and in this paper, the author introduced hypergeometric functions of the generalized zeta function, which is defined by zeta lambda mu x y z a equal to the right hand side. And this right hand side, you can see that this is the product of mu and phi, where this mod of x is less than 1, mod of y is less than 1, mu is given with the condition. So here you can see the condition for mu, lambda, and a. And this phi is already defined. This is called Rubit left zeta function, which was earlier defined by question 1.3. In this way, we have this type of hypergeometric series, which was given in 2009. Then next, on the same paper again, we have an alternative representation. And this alternative representation is given by zeta lambda mu x y z a equal to the right hand side is given in terms of phi mu star. Here this phi mu star is the generalized zeta function divided by 1.5, followed by changing the order of and considering equation 1.5. Now the case y equal to 0, if you consider, then this is simply given by the long function that is phi mu lambda star x z a. It is generalization of the zeta function, defined by 1.5. The further generalization of a left zeta function was given by various others. So here, first of all, let us consider one generalization which is given by m gun and k gain with SL Galla. This is the published number in the liberal group geometry in the year 2008. This is one of the generation of zeta function. And here you can see that the upper parameters are given by lambda, lower parameters, lower, let me say, denominator is given by a plus n to the power of that. So this is one of the generalization given by Merlaga and others. We will keep in mind this type of generalization, and based on all these generalizations, we will be extending our problem to bivariate function. For that purpose, actually, we have to use another type of integral representation for the beta function. And one of the generation is given in the following form, which is could be a one generation. Here, 1D is exponential of minus p upon p into 1 minus p is added to the ordinary beta function, and this is defined in such a way that this may be corrected to Macron function, error function, the Decker function, and so on. And this is, in fact, a generalization of the ordinary beta function. It is given by Bxy. As to this type of generalization of beta function, you can find in many papers of Chaudhary and others. And here, depending on this, you can use hypergeometric function in such a way that the bivariate generative functions can be obtained. And for this purpose, we have to define this Gauss hypergeometric function array in another way, that is FPABCS. And this is the way in which we can define this is done by one point here. Then second one is the function given by 5a. Again, given the same parameter is variable x, and this is given in terms of the equation 1.12. So these are two declarations of the hypergeometric function which will be used in our case. And here we will keep in that there are various equations which are given in the literature, and one of this is 1.13, which is used for periodic functions. Another 1.14, which is used for exponential function, and the third one is 1.15, which is again used for hyperbolic cosine function, that is given by the integral function given by 1.15. Here 1.13 to 1.15 can be obtained by using cos square beta.
Sound is low.
Hmm?
Sound is low. Sound is not coming proper.
Some 1 minute PG.
Sir, you just come close to the mic. That is why it is less audible.
Sorry?
Sir, you just come close to the microphone. That is why. I think the mic is some far away.
Maybe. Okay. Okay. Right. Okay, so these are three integral representations. And next, we can say that this is an extension of order Zeta function, which is used here to define the extended Zeta function given in the form of double series and represented by 2.1. So this is one of the representation of the real Zeta function, which can be said to be having Hypergeometric form, and another alternative representation in the Hypergeometric form is given by this relation 2.2, that is zeta nu lambda star, and again x y z a b are there, where this phi is the generalized zeta function defined by 1.3, and this is solved by changing the order of summation and considering definition 1.3. So just this is Hamilton type derivative function of the function phi defined by 1.3. Now several special cases of such extension are given, and we can see that this is reducible to zeta za by yza by delta mu xza by delta lambda star xza by delta x star xza, and the last one is zeta lambda delta x y z a. So these are the relationship we can say for special case. Unless the case of y equal to 0, then definition 2.1 suggests that this can be done in the following way. And here, this generalization of the zeta function is given as zeta mu lambda delta mu. Where the case when p equal to 0 of the definition 2.1 gives us another generalization of the zeta function that is given by pi lambda mu, and this is given by the double series.
सर सर वॉइस थोड़ा क्लियर नहीं हो रहा सर वॉइस थोड़ा क्लियर नहीं है सर
वॉइस क्लियर नहीं है
हाँ थोड़ा सा नजदीक मैं थोड़ा बोलिए
अरे बिल्कुल
माइक के पास थोड़ा
1 minute let me check again.
सर माइक्रोफोन यूज करिए
Mute. Hello?
Yes, sir.
हाँ,
Now,
okay,
audible?
okay.
हेलो
हाँ,
अभी
audible?
तो हाँ, अभी तो कुछ ठीक आ रहा है.
Okay, okay. So here we can see that the case when p equal to 0, in the definition gives us another generation of the zeta function, which is given by 2.10. All right, now based on the definition 2.11, we have the following relation that is given by 2.12, and in the case when lambda equal to rho equal to 0, we have the following double series, and this is the representation for zeta mu star. Now the case when y equal to 0, then simply we are having this 2.10. All right, here this is the corollary now, and why we say that this is by zeta function. So therefore this can be given by at equation 2.13. Here you can see that this right hand side is the product of two Gauss functions, and Gauss functions are containing x and y, and this is the representation for this zeta function. That means we can see that this relationship will actually be giving us as a special case the following is given by phi y1a equal to a to the power minus 1 2 upon a1 a plus 1 y. 1 2 upon a1 a plus 1 y. Already you can see that this is the product of phi and fp. So this left hand side is again zeta function, and another relation is the zeta function, but the right hand side is containing a function that is given by 3f2. Next, yeah, these are derivatives simply, and depending on these derivatives, we have written this corollary 2.3, and here again you can see that right hand side is containing phi as well as phi p and derivative of x. Next we have another relation that is given by phi yz a equal to, and this that this is the result which is containing logarithm of 1 upon y, and in second part you see that is log of y. So this is a typical type of example which is is obtained for this Hurwitz-Lutz zeta function. Now, there is one term 2.1 because now time is going. So let me just consider this theorem 2.1. Here you can see that the left hand side of Riemann zeta function can be given in terms of Fp and another term which is again containing this Riemann zeta function. This is again a result and is obtained from the earlier one 2.19 by simply writing now rho equal to 0. And this is result which was given by Garg and others. And already I have shown you the reference. Finally, I come to the end of the lecture, and these are the references. In fact, all the references which I have used are already shown in my slides. So this is all. Thank you.
So I request audience if they have any query or want something from the Professor Pathan.